Moscow, 1944. In a secret hangar east of the Urals, 3 Soviet engineers stared at the remains of a P-51 Mustang, shot down over German territory and recovered by the Red Army. The metal gleamed under the industrial lamps with a silvery tone none of them had ever seen before in combat-grade steel. The wing seams were welded with a precision that defied everything they knew about mass production. But what truly kept them awake at night was not the fuselage structure nor the hydraulic system. It was the engine, a Rolls-Royce Merlin built under American license by Packard, with pistons that had endured more than 300 hours of maximum power flight without cracking. The team leader, a metallurgist named Andrei Tupolev Jr., ran his fingers along the cylinder surface and felt something strange, something Soviet manuals never mentioned. The steel did not have the fatigue marks it should have after so much time in combat. It was as if the material had strengthened with use instead of weakening. If they managed to understand this and replicate it, the Soviet Union could build engines superior to anything flying over Europe or Asia. But if they failed, Stalin would not forgive the waste of resources during wartime. The order had already come from the Kremlin. Copy the engine exactly. No changes, no improvisations, no excuses. And that same order, Tupolev thought, if he wiped oil from his hands, could become a death sentence for everyone in that room, because no one in Moscow yet understood that copying American technology was not merely a matter of blueprints and measurements, but something far deeper. An industrial philosophy the Soviet Union had never developed. The Americans did not build engines to last one war. They built them to last 1,000 wars. And that difference, invisible in technical drawings, was about to shatter everything Soviet engineers believed about metallurgy. The paradox was simple but deadly. The Merlin blueprints showed manufacturing tolerances so strict that no Soviet factory could achieve them, and specified steel alloys so advanced that there weren't even Russian names for them. Tupolev had spent 3 sleepless nights disassembling the engine piece by piece, measuring every component with German imported calipers, writing down every micron of difference between what the plans demanded and what the physical metal revealed. What he discovered terrified him. The cylinders were made from an alloy containing nickel, chromium, and molybdenum in proportions requiring high-temperature furnaces with controlled atmospheres, equipment that existed in only 3 factories in the entire United States. The pistons used compression rings treated with a process called nitriding, which hardened the surface without weakening the core, something the Soviets had only seen in captured German experimental prototypes. But the most unsettling thing was consistency. Every engine part, from screws to connecting rods, had been manufactured with tolerances under 1/10 of a millimeter. In Soviet factories, where workers labored 18-hour shifts with worn tools and irregular calibration, achieving such precision in one piece was difficult. Achieving it in 50,000 pieces per month was impossible. And Stalin did not understand the word impossible. When the preliminary reports reached the Kremlin, the response was immediate and brutal. You have 6 months to produce the first functional engine. If you fail, you will be replaced. The threat was clear. In the Soviet Union of 1944, being replaced did not mean a job change. It meant a train to Siberia or a basement in Lubyanka. Tupolev knew he had 2 options: lie about what was technically possible and risk a public disaster when the engines failed in flight, or tell the truth and be accused of industrial sabotage. He chose a third path: try the impossible and document every failure so precisely that if he died, at least the next generation of engineers would understand why. Before the war, the Soviet aviation industry had built its reputation on 2 principles. functional simplicity, and mass production. The designs of Ilyushin, Yakovlev, and Lavokin followed the same philosophy: rugged engines able to run on low-quality fuel, welded steel structures repairable in the field with basic tools, and mechanical systems with no complex electronics that could fail in Siberian cold. This philosophy had worked brilliantly during the early war years, when the Luftwaffe underestimated Soviet capacity to produce aircraft faster than they could be destroyed. But in 1944, when the P-51 Mustangs began escorting Allied bombers over Berlin with a range of more than 1,600 kilometers without refueling, Kremlin strategists realized something disturbing. Americans were not playing the same game. They did not build aircraft to survive. They built aircraft to dominate. And the difference was in the engines. The American Merlin produced 1,000 horsepower continuously for more than 300 hours before needing major maintenance. The best Soviet Klimov and Shvetsov engines produced between 1,000 and 1,100 horsepower, but required complete overhaul every 100 hours. This difference seemed technical, almost abstract, until translated into operational reality. An American pilot could fly 30 missions before his engine showed fatigue. A Soviet pilot had to change aircraft every 10 missions. The consequence was psychological. Americans built confidence in their machines. Soviets built distrust. That distrust permeated the designs themselves. Soviet engineers always designed assuming something would fail, adding redundancies and reinforcement. Americans designed assuming everything would work as planned, optimizing weight and efficiency. Two philosophies, two industrial worlds, two ways to build a machine of war. When Tupolev received the first special steel ingots from the Magnitogorsk foundries, he immediately knew the project was doomed. The Soviet steel had the right color and approximate hardness, but tensile and fatigue tests were disastrous. The material cracked after just 50 heating-cooling cycles, while the American steel endured more than 500 without plastic deformation. The difference was not only chemical composition, but manufacturing process. Americans used electric arc furnaces with argon atmospheres to avoid oxidation, then quenched steel in precisely controlled oil baths. Soviet foundries used coal furnaces exposed to atmospheric air, introducing oxygen and nitrogen impurities that weakened the metal, and cooled pieces in open air due to lack of quenching tanks. On paper, the Soviet steel matched specifications. In practice, it failed unpredictably. Tupolev wrote a 17-page report explaining the differences and recommending redesigning the engine to fit Soviet industrial capabilities. The report never reached Stalin. A political commissar intercepted it, saw it as an admission of incompetence, and sent a 3-line summary to the Kremlin. Engineer Tupolev requests modifications because he does not trust Soviet workers. 2 days later, the NKVD paid him a visit. He was interrogated for 6 hours about defeatist tendencies and excessive admiration for capitalist technology. He was not arrested, but was assigned a political supervisor who had to approve every technical decision. From that moment, Tupolev understood that his job was no longer to build a functional engine. It was to build the illusion of progress until someone more powerful decided what to do with the disaster. The first prototype was completed in March 1945, 3 weeks before the fall of Berlin. It was assembled with hand-selected parts, each inspected under magnification. The engine looked identical to the original. But within 30 seconds of testing, the difference between appearance and reality became obvious. It started with an uneven roar. Cylinders misfired. The oil overheated within minutes. At 5 minutes, a piston developed a microcrack. At 8 minutes, the engine seized with a metallic snap that made everyone step back. The autopsy revealed accelerated wear, deformed compression rings, and connecting rods with fatigue cracks. The problem was not assembly. It was Soviet steel failing under stresses the American design assumed were trivial. Tupolev submitted another report, this time with photographs and calculations. This one reached the Kremlin, but was read by Lavrenti Beria, head of the NKVD. His response was concise and terrifying. Build 100 more engines. If all fail the same way, we have evidence. If one works, we have success. Engineers who fail 3 times will be reassigned. In the next 6 months, Soviet factories produced 237 Merlin copies with variations in metallurgy, heat treatment, and tolerances. Some used tungsten to compensate for lack of molybdenum. Some were quenched in salt water. Some used Swedish steel obtained through clandestine channels. None matched the American original. Engine number 43 ran 17 hours before failing. Engine number 89 ran 23 hours. Engine number 142, built with imported Swedish steel, ran 41 hours. A hidden chart showed the real problem. The ceiling was not technical skill or incomplete blueprints. It was America's entire industrial infrastructure. The U.S. had pure Minnesota ore, precision-built furnaces, standardized supply chains. The USSR had impure Ural ore, furnaces designed for structural steel, and chaotic logistics. Systems cannot be copied with blueprints. In October 1945, with the war over, Tupolev was allowed to visit a Packard factory in Detroit. What he saw confirmed everything. Packard was not a factory. It was an ecosystem. Tools calibrated weekly. Workers trained for 6 months before touching parts. Steel certified to 5 decimals of chemical composition. Every engine tested 4 hours at full power. Engines failing tests were fully scrapped, not repaired. In the USSR, scrapping a nearly complete engine would be criminal sabotage. In America, it was standard quality control. Tupolev knew none of that could be implemented in the Soviet system, not because it was technically impossible, but because it required a cultural shift the USSR would never allow. The project was quietly cancelled in 1946, but the lessons survived. The failed engines were used in test aircraft. The metallurgy data shaped new research. The engineers, including Tupolev, were reassigned to jet engine programs, where they encountered the same limits on an even larger scale. But something had changed. They no longer assumed foreign technology could be copied simply by acquiring blueprints. They learned that advanced technology rests on layers of infrastructure, tacit knowledge, and organizational culture that cannot be transferred through documents. This led to a new strategy. Instead of copying American designs, the Soviets built engines suited to their own industrial reality, simpler, more robust, more tolerant of low-quality fuel, easier to maintain. Not superior in absolute quality, but superior for their environment. Declassified archives showed Stalin was informed of the failure in 1946, but did not punish the engineers. Not out of compassion, but pragmatism. He finally understood the issue was not incompetence, but structural limits. He reportedly told Beria, "The Americans did not beat us with better scientists. They beat us with better factories." This insight reshaped Soviet strategy. Instead of matching American quality piece for piece, they focused on quantity and innovation in fields where they had structural advantages: rockets, heavy tanks, long-range artillery. The Soviet space program, first satellite, first human in orbit, rose directly from the lessons of the failed Merlin project. Their rocket engines were simpler, less efficient, but cheaper and faster to iterate, giving them an early advantage in the space race. Ironically, the failure to copy a 1940s piston engine helped fuel the success of 1950s and 1960s Soviet rockets. In 1953, 7 years after the Merlin project ended, Andrei Tupolev Jr. lectured at the Bauman Institute in Moscow. His talk circulated secretly for years. He explained every phase of the project, every failure, every discovery. But engineers memorized his final words. Technology does not exist in a vacuum. Every screw, every alloy, every tolerance is the result of decades of decisions about how to organize factories, train workers, and define quality. When we copied the Merlin blueprints, we tried to copy 50 years of American industrial history in 6 months. It was like trying to learn a language by copying a dictionary without understanding the grammar. The Americans did not build a better engine. They built a better system to build engines. And one day, we must build our own system, not copy theirs. These words shaped a generation of engineers, even as Soviet industry remained limited and resistant to deep structural reform.